Hello learners, I am Dr. R.B. Malati, Assistant Professor at Chhattisgarh Swami Vivekanand Technical University, Bhilai. I welcome you all again to the course Essentials of Surveying Application and Techniques. Let us continue our discussion on tachyometry. In the last class, we talked about the analytic lenses, and while giving the overview, I mentioned that if the multiplying constant is 100 and the additive constant is 0, the horizontal distance is obtained by simply multiplying the staff intersect by 100. Today, we will understand the theory behind it first by step calculation. Then we will move to the tangential method of tachyometry, which is another important method to learn. So, let us start our today's session. So, imagine you are using a theodolite. Now, looking through the telescope of the theodolite, you want to calculate the distance between the theodolite and a measuring staff placed at a certain point. Normally, calculating this distance could be difficult, and so the analytic lenses are provided in the telescope between the object lens and the eyepiece to make the distance calculations much easier. Let us see how it is done. So, the figure shown here gives a theory of the analytic lens. Let us understand the key terms first. AB is where we place the measuring staff. S is the distance you measure on the staff, that is the stadia intercept. A dash, B dash is the image of the staff that would form if the analytic lens wasn't there. O is the center of the object lens in the theodolite. K is the distance between the analytic lens and the object lens. F1 and F2 are the focal lengths of the object lens. That is how far the lens brings light into focus. C is the center of the analytic lens. CO is equal to F1 and CO dash is F2, the conjugate focal distance of the analytic lens. And now let us see how the rays of light travel. When light comes from points A and B to the theodolite, one of them passes through the outside principal focus of the object glass and emerges parallel to the axis of the telescope. The other ray travels in a straight line through the optical center of the object glass. When these rays hit the analytic lens, they bend and create a new image. Without the analytic lens, the image would have formed at A dash, B dash, but because of the lens, the new image forms at AB. From the laws of lens, we can write equations for object lens and analytic lens. So, first, lens equation for the object lens is 1 by f is equal to 1 by f1 plus 1 by f2, and lens equation for analytic lens is 1 by f is equal to 1 by small f1 minus 1 by small f2. Notice a minus sign here. This is because the image and the object are on the same side of the lens. Now, remember, A dash, B dash is old image and AB is a new image. We want to understand the relationship between them. So, using similar triangles property for the triangles ABO and A dash, B dash O, that is the image formed by the object lens, we have S by I is equal to capital F1 by capital F2. Here, S is the stadia intercept, that is the measured part on the staff, and I is the distance of the image formed by the object lenses. Again, using the similar triangles property for the triangle A dash, B dash, C and ABC, that is the image formed by the analytic lens, we have I by I dash is equal to small f2 by small f1. This tells us how the image size changes after passing through the analytic lenses. Now, from S by I is equal to F1 by F2, we get capital S is equal to F1 by F2 into I. And from I by I dash is equal to F2 by F1, we get I is equal to F2 by F1 into I dash. Substituting for I in the S equation, we get S by I dash is equal to capital F1 by capital F2 into small f2 by small f1. So, we need capital F1 by capital F2 and small f2 by small f1. This capital F1 by F2 can be obtained from object length equation, and small f2 by small f1 can be obtained from the length equation. Let us see how to get capital F1 by capital F2 first. From the object length equation, 1 by f is equal to 1 by f1 plus 1 by f2. We rearrange and solve for f1 and f2. So, we get f1 by f2 is equal to f1 minus f by f. This can be written as capital F2 is equal to capital F1 capital F by capital F1 minus capital F. Now, let us see how to get small f2 by small f1. From the analytic length equation, 1 by f is equal to 1 by f1 minus 1 by f2. We invert the equation to express f2 in terms of f1 and f, and we arrive at small f2 is equal to 1 by f1 minus 1 by f, which can be rewritten as f2 is equal to 1 by f minus f1 by f1 into f. Now, taking the reciprocal, we arrive at f2 is equal to f1 f by f minus f1, which gives f2 by f1 is equal to f by f minus f1. Now, if we introduce f2 minus k to represent any additional distance between the focal point and the position of the analytic lens, the expression becomes f2 by f1 is equal to f plus capital F2 minus k by small f. Substituting the values of f1 by f2 and small f2 by f1 into the equation S by I dash, we get S by I dash is equal to f1 minus f by f into f plus f2 minus k by f. Simplifying this, we get S is equal to I dash into f1 minus f by f into f plus f2 minus k by f. Now, S by I dash is equal to f1 minus f by f into f plus f2 minus k by f, and when we substitute the value for f2, we get S by I is equal to f1 minus f by f into f plus capital F f1 by f1 minus f into k by f. Then, taking the LCM and bringing f into capital F1 minus f leads to S by I dash is equal to f1 minus f by f into small f into f1 minus f plus f f1 minus k into f1 minus f divided by f into f1 minus f. Now, taking f and k inside leads to S by I is equal to f1 minus f by f into small f capital F1 minus f square plus f f1 minus k f1 plus kf by f into capital F1 minus capital F. Then cancelling f1 minus f from both the denominator and the numerator leads to S by I dash equal to f1 into f plus f minus k by ff plus f into k minus f by ff. Then taking S by I dash to the right and f1 f plus f minus k by ff. To the left, we arrive at f1 f plus f minus k by ff is equal to s by I dash minus f into k minus f by ff. Now, from this we can determine f1. So, f1 is equal to s by I into ff by small f plus f minus k minus capital F into k minus f into ff by ff into f plus f minus k. Then cancelling ff, we finally arrive at the equation f1 as s by I into ff by small f plus f minus k minus f into k minus f by f plus f minus k. Now, to calculate the horizontal distance capital D between the instrument and the staff, we use this formula D is equal to Fn plus D. So, substituting the value of f1 here, we get capital D is equal to s by I dash into ff by small f plus capital F minus k minus capital F into k minus f by small f plus capital F minus k plus D. Now, the condition that distance D should be proportional to the intercept S requires the factor capital F into k minus f by small f plus f minus k plus D to be 0. So, minus f k minus f by small f plus capital F minus k plus D will be equal to 0, from which we arrive capital F into k minus f by small f plus f minus k is equal to D. From this, we arrive by means of mathematical calculation the value k. K is equal to small f plus f d by f plus D. Next, by adopting suitable value of capital F, f, I dash and k in the first term, that is in the term capital F by I dash into f plus f minus k, it is equal to 0. Therefore, D is equal to 100s. From equation, it is seen that if the theodolite is fitted with an analytic lens, the horizontal distance between the instrument axis and the staff position is obtained by multiplying the staff intercept by the multiplying constant. And I believe this step-by-step calculation gave you the knowledge how it is arrived. Let us now move to the second topic of discussion of the day, that is the tangential method of tachymetry. Let us have a small recap of what we read about tangential method in our first lecture on tachymetry. The tangential method, unlike the stadia head method, does not require stadia heads. In this, we measure the horizontal and vertical distance from the instrument to the staff station by measuring angles to two targets that are placed at a known distance apart on a staff. And depending upon the vertical angles, three cases may arise. First is both vertical angles as elevation angles, that is, both observed vertical angles are upward from the instrument. Next, both vertical angles as depression angles, that is, both observed vertical angles are downward from the instrument. Third, one angle is elevation and the other as depression, that is, one vertical angle is upward and the other is downward from the instrument. Now, let us look into the first case where both vertical angles are angles of elevation. For this, imagine A and B represent two targets fixed s meters apart on a staff held vertical at D. Let C represent the Trunian axis of the theodolite and alpha 1 and alpha 2 be the angles of elevation to the targets A and B respectively. and h is the horizontal distance between the instrument station C and the staff station D, and v the vertical distance between the instrument axis and the lower vane capital AE. Here S is the distance between the vanes, that is the staff intercept capital AB. Now, our goal is to find two things: the horizontal distance between the instrument at point C and the staff at point D, which we will call capital H, and next the elevation. Now, let us first look into the horizontal distance formula. From the triangle ACE, we get CE is equal to AE cot alpha 1, and from triangle BCE, we get CE is equal to BE cot alpha 2. Comparing the above two equation, we get AE cot alpha 1 is equal to BE cot alpha 2. And we know BE is nothing but AE plus AB. So, we can write AE cot alpha 1 is equal to AE plus AB cot alpha 2. So, multiplying the cot alpha 2 inside, we arrive at AE cot alpha 1 is equal to AE cot alpha 2 plus AB cot alpha 2. Here, AB is equal to yes. So, we can write AE cot alpha 1 is equal to AE cot alpha 2 plus S cot alpha 2. Now, taking the cot alpha 2 of AE to the left side, we get AE cot alpha 1 minus cot alpha 2 is equal to S cot alpha 2, from which we can get AE is equal to S cot alpha 2 by cot alpha 1 minus cot alpha 2. We know cot is 1 by tan. So, AE is equal to S into 1 by tan alpha 2 by 1 by tan alpha 1 minus 1 by tan alpha 2. Now, taking the LCM and solving the denominator, we arrive at AE is equal to S by tan alpha 2 by tan alpha 2 minus tan alpha 1 by tan alpha 1 tan alpha 2. From this, we get capital AE is equal to S by tan alpha 2 into tan alpha 1 tan alpha 2 by tan alpha 2 minus tan alpha 1. Now, cancelling tan alpha 2 both on the numerator and the denominator, we arrive at AE is equal to S tan alpha 1 by tan alpha 2 minus tan alpha 1. We know H is equal to AE cot alpha 1 from the triangle ACE, and therefore H is equal to S tan alpha 1 by tan alpha 2 minus tan alpha 1 into cot alpha 1. Now, cancelling this tan alpha 1 on both the sides, after substituting cot alpha 1 by 1 by tan alpha 1, we arrive at the equation H is equal to S by tan alpha 2 minus tan alpha 1. We know tan is equal to sin by cos. H is equal to S by sin alpha 2 by cos alpha 2 minus sin alpha 1 by cos alpha 1. With this, upon mathematical calculation, we get H is equal to S cos alpha 2 cos alpha 1 by sin alpha 2 cos alpha 1 minus sin alpha 1 cos alpha 2. Since sin A minus B is equal to sin A cos B minus sin B cos A, we can write H is equal to S cos alpha 2 cos alpha 1 by sin alpha 2 minus alpha 1. Therefore, H is equal to S cos alpha 2 cos alpha 1 cosine of alpha 2 minus alpha 1. Finally, now let's figure out the reduced level of the point D where the staff is standing. We already know that reduced level of D is equal to RL of the Trunian axis plus EA minus AD. And we have previously found that AE, which is also equal to EA, is equal to S tan alpha 1 by tan alpha 2 minus tan alpha 1. Thus, the formula for the reduced level of D becomes RL of D is equal to RL of the Tunian axis plus S into tan alpha 1 by tan alpha 2 minus tan alpha 1 minus height of the lower target above. This is the exact elevation of the point T, considering both the horizontal distance and the height difference using the angles measured by the theodolite. Moving to the next case, that is both vertical angles may be depression angles. Imagine we are looking at 2 points on a staff that someone is holding in front of you, but instead of looking up at the points, you are looking down because both points are lower than your line of sight. This situation uses what we call depression angles, where you are looking downward instead of upward. Now, let us figure out how far that staff is from you are standing, which we will call it the horizontal distance. We are also going to figure out the height difference between where you are and where the staff is. So, from triangle ACE, we get CE is equal to, which is also called H is equal to AE cot alpha 2. And from triangle BCE, we get CE, which is also called H, is equal to BE cot alpha 1. Now, comparing both the equations, we get AE cot alpha 2 is equal to BE cot alpha 1. So, this leads to AB plus BE cot alpha 2 is equal to BE cot alpha 1, because AE is equal to AB plus BE. Now, taking the cot alpha 2 inside, we get AB cot alpha 2 plus BE cot alpha 2 is equal to BE cot alpha 1. This results in AB cot alpha 2 is equal to BE cot alpha 1 minus cot alpha 2. Here, AB is S. So, substituting that, we arrive at BE cot alpha 1 minus cot alpha 2 is equal to S cot alpha 2. And this leads to, so BE is equal to S into 1 by tan alpha 2 by 1 by tan alpha 1 minus 1 by tan alpha 2. Now, taking the LCM and solving the denominator, we arrive at BE is equal to S by tan alpha 2 by tan alpha 2 minus tan alpha 1 by tan alpha 1 tan alpha 2, which leads to BE is equal to S by tan alpha 2 into tan alpha 1 tan alpha 2 by tan alpha 2 minus tan alpha 1. Cancelling tan alpha 2 both on the numerator and the denominator, we arrive at BE is equal to S tan alpha 1 by tan alpha 2 minus tan alpha 1. We know H is equal to BE cot alpha 1 from the triangle BCE. So, H is equal to S tan alpha 1 by tan alpha 2 minus tan alpha 1 into cot tan alpha 1. Substituting for cot, H is equal to S tan alpha 1 by tan alpha 2 minus tan alpha 1 into 1 by tan alpha 1. Therefore, H is equal to S by tan alpha 2 minus tan alpha 1. We know tan is sine by cos. So, H is equal to S by sine alpha 2 by cos alpha 2 minus sine alpha 1 by cos alpha 1. Upon doing the mathematical calculation, we get H is equal to S cos alpha 2 cos alpha 1 by sine alpha 2 cos alpha 1 minus sine alpha 1 cos alpha 2. We know sine A minus B is equal to sine A cos B minus sine B cos A. Therefore, H is equal to S cos alpha 2 cos alpha 1 by sine alpha 2 minus alpha 1. This finally gives a solution h is equal to s cos alpha 2 cos alpha 1 cosine of alpha 2 minus alpha 1. Now, let us calculate the reduced level of the point D. The reduced level of D is equal to reduced level of the Trunnion axis minus EB minus BD, which is equal to reduced level of the Trunnion axis minus S tan alpha 2 by tan alpha 2 minus tan alpha 1 minus height of the upper target above D. Moving to the case 3. One of the angles may be an elevation angle and the other may be the depression angle. In this situation, we are working with two angles. One is the elevation angle, meaning it is pointing upward, and the other is a depression angle, meaning it is pointing downward. The goal is to calculate the horizontal distance and the elevation difference between the instrument and a point on the ground where the staff is placed. From triangle ACE, we get CE is equal to H is equal to AE cot alpha 1, and from triangle BCE, CE which is also equal to H is equal to BE cot alpha 2. Comparing these two equations, we get AE cot alpha 1 is equal to BE cot alpha 2. We know BE is equal to S minus AE. So, substituting in this equation, we get AE cot alpha 1 is equal to S minus AE cot alpha 2. Now, taking the cot alpha 2 inside, from this AE cot alpha 1 plus cot alpha 2 is equal to S cot alpha 2. This results in AE is equal to S cot alpha 2 by cot alpha 1 plus cot alpha 2. We know cot is equal to 1 by tan. So, AE is equal to S into 1 by tan alpha 2 by 1 by tan alpha 1 plus 1 by tan alpha 2. Now, taking the LCM and solving the denominator, we get AE is equal to S by tan alpha 2 by tan alpha 2 plus tan alpha 1 by tan alpha 1 tan alpha 2. This leads to AE is equal to S by tan alpha 2 into tan alpha 1 tan alpha 2 by tan alpha 2 plus tan alpha 1. From this, we get AE by cancelling the tan alpha 2 from the numerator and the denominator is tan alpha 1 by tan alpha 2 plus tan alpha 1. We know H is equal to AE cot alpha 1 from the triangle ACE. Therefore, H can be written as H is equal to S tan alpha 1 by tan alpha 2 plus tan alpha 1 into cot alpha 1. Cot is 1 by tan. Therefore, H is equal to S tan alpha 1 by tan alpha 2 plus tan alpha 1 into 1 by tan alpha 1. This leads to H is equal to S by tan alpha 2 plus tan alpha 1. Tan is sine by cos. Therefore, H is equal to S by sine alpha 2 by cos alpha 2 plus sine alpha 1 by cos alpha 1. Upon mathematical calculation, we can write H is equal to S cos alpha 2 cos alpha 1 by sine alpha 2 cos alpha 1 plus sine alpha 1 cos alpha 2. Sin A plus B is sin A cos B plus sin B cos A. Therefore, H can be written as S cos alpha 2 cos alpha 1 by sin alpha 1 plus sin alpha 2. Finally, H is equal to S cos alpha 2 cos alpha 1 cosine of alpha 1 plus alpha 2. Now, let us calculate the reduced level of the point D. So, reduced level of the point D is equal to reduced level of the Trunnion axis minus AE minus AD. We know AE is equal to S tan alpha 1 by tan alpha 2 plus tan alpha 1. Therefore, reduced level of D is equal to reduced level of the Tronian axis minus S tan alpha 1 by tan alpha 2 plus tan alpha 1 minus height of the lower target above D. So, we have derived formulas to calculate both the horizontal distance h and the elevation difference using the angle of elevation and depression. Hope you understand this. The one thing that I want to say here is the tangential method in tachymetry isn't very popular because it is slow and requires lots of calculation, making it prone to more mistakes. You have to measure two vertical angles to determine the distance, which means double the efforts for one result. Again, the instrument might shift slightly while you are taking the measurement, which can affect the accuracy. These issues makes a tangential method less favored compared to the stadia method, where using a staff held vertically is quicker and easier. So, if you are using a theodolite, kindly stick with the stadia hair method as it is a better choice. So, to conclude the class, in today's class, first we learned the theory behind D is equal to 100S of the analytic lens. Then we derived important formulas for the three cases of tangential method in tachymetry. In our next class, we will continue our journey in tachymetry by solving good number of example problems. We will also look into the next stadia method, that is the mobile hair method. Also, we will discuss common sources of errors. And finally, I will conclude by summarizing the procedure for conducting a tachymetric survey. I would like to keep it last for you to clearly visualize the procedure. So, thank you for your attention and happy learning.